Good morning, everyone. Welcome to the Easy Power Thursday webinar series. My name is Jim Chastain. I'm your host for today's session, and we're looking forward very much to the presentation by Dr. Bob Hansen from ABB. And before we do that, as is our custom, we'd like to run a couple poll questions that will give us some perspective as far as the audience leaning. So again, thank you very much. And without obligation or liability, we appreciate your helping us out with this poll question. That is, the National Electrical Code has a definition of selective coordination that applies to short circuits, overloads, and ground faults. And that is a true or false question. We will be doing a Q&A session at the end of the presentation. So during the presentation, feel free to enter questions in the question box of the webinar control system. It looks like we have close to a quorum. Let's leave this up open another 10 seconds. A couple late arrivals, good. All right. Here's how people have responded to this one. Looks like trues have it 4-1. Fair enough. And now the next is, how often do you refer to selective coordination tables in the vendor database? This one, very curious to see how folks respond. It's ironic, we in this information age, we think if we put anything on the internet, everyone has access to it. Consequently, everyone knows it, which is not always the case. So it's part of kind of sorting this out from a marketing point of view. Looks like we have close to a quorum here. So let's see how folks have responded here. Pretty good distribution. Again, thank you for participating, and welcome to the presentation. The presenter today comes with severe experience. I think that will benefit us all, and we're looking forward to his presentation. Bob, let me hand the presentation over to you, and you can share your screen. Mr. Bob Hansen.
Okay, thank you. So Jim, thank you very much. Thank you to Easy Power for allowing me to share this information with everybody. And thank you everybody for attending. My name is Bob Hansen. I am a field application engineer with ABB. And today's topic is really selected by me out of questions that I commonly get and encounter during previous presentations such as this, or during conversations with a variety of folks in the industry. So this is what I've got planned for today. Just want to make sure we're all talking about using the same definition, so reading off the same sheet of music, so to say. So I'll just do a quick review of what some of the key things the NEC requires and definitions, and then jump into these various topics in terms of specifying selective coordination, some details on coordinating circuit breakers, and then even further details on how to do that across low voltage general purpose transformers. What do you do when a circuit breaker has ground fault? And then talk a little bit about circuit breaker ratios. Okay, so I'll start with just, again, some of the basics here. There is, of course, I think you're all aware, a formal definition of selective coordination that appears in the code. That, of course, is in the section for definitions under Article 100. And then there's another, not a definition, because obviously it is in Section 100, under Article 517.31, that is more of a, for lack of a better term, a definition by usage, where it's referring to 0.1 second coordination. So let's just touch a little bit on each of these. So the formal definition in the code, selective coordination, its intent is, for most part, universally accepted as meaning only the first device upstream of the fault would clear that fault, leaving the remainder of the system unaffected. As the polling question showed, there's still some interpretation differences in this, and I feel those come about from the fact that the term overcurrent may not be defined in the NEC. I feel it is defined in other IEEE literature, and again, for the 80% that voted that this definition does apply to overloads, short circuit, and ground fault, I think then you're using the same definition I would of overcurrent. If you're in the 20% that doesn't agree with this, then I guess the conversation continues, but this is the assumption I'm working under today with anything I discuss, that when we're talking about this definition of selective coordination, we're talking about any possible type of fault current out to the maximum available fault current on the system. Now, under Article 517 for healthcare systems, this is the most recent statement of that, but pretty much a similar statement since 2014 appeared for, again, Article 517 systems. This states the requirement differently than the formal definition of selective coordination up above, in that for, again, essential systems of a healthcare facility, coordination up to the point of 0.1 second and beyond is what's required. So in other words, this statement is saying that if the fault occurs below 0.1 seconds and were to be cleared below that, we're not worried about coordination. The industry has adopted a term for the formal definition, the Article 100 definition, in calling that 0.01 seconds, so 0.01 second coordination. That kind of visually, when you're reading it, perhaps distinguish it quickly from 0.1 second requirements. Realize that 0.01 second coordination is, again, I feel been an industry adopted term. It's used widely in specifications, but it's technically not correct. It almost sounds like it's to the exclusion of coordination between 0 and 0.1 seconds, and that's not the intent. It's just, again, an industry adopted term to indicate the application of this definition. So I'm going to use 0.01 second coordination and the term selective coordination interchangeably to mean coordination throughout the complete range of available fault current for any type of fault. And examples of systems requiring selective coordination, more specifically, right, Article 700, 701, legally required standby, 708, critical operations power systems, and those associated articles for those sections. We mentioned 517 for essential systems in hospitals. Another example, elevators and other associated Article 620 equipment. And of course, there are more areas of the code that make statements about selective coordination requirements. But these would be some of the most common ones that you see in many designs and facilities. Okay, so with that kind of quick background, let me jump into the various common questions, and in some cases, maybe misconceptions. Selective coordination of circuit breakers. I think most folks who are in design and doing typical commercial systems, institutional systems, know circuit breakers can coordinate. But if you haven't done that type of work, you may still look at time current curves and see breakers that are overlapping and wondering, well, how can those possibly coordinate if they're overlapping? So let's address the question. Can circuit breakers coordinate even though they overlap in the instantaneous region? And if so, how do I determine if a circuit breaker pair coordinates? Well, the upfront answer to that is yes, the circuit breakers can coordinate, but let's work our way slowly to that point. So it helps, the way I like to discuss it is just recognize kind of there are two major parts to a time current curve when we're talking coordination. So I've got two electronic trip circuit breakers laid side by side in the plot you see on the right, and the various numbers at the different breakpoints between a pickup and a delay. And if we were to look at, say, this first shaded area, kind of from 0.4, where I transitioned from short time to instantaneous, if I look at that and from that point above, I would say, well, if I can just separate the breakers, then from 0.4 and above, I can say they're separated. they're coordinated because I have that separated with something called white space from the old age of using onion skin plots. So I call this kind of the non-instantaneous region, or what some NEMA documents might call the overload region. So that's a separate technique, a separate skill to determine coordination in this zone. Now, once I go down below 0.4 and I deal with the instantaneous part of the protection, and especially that pesky foot of the breaker that tends to overlap in most cases, with some exceptions, it's really a different skill set to know how to get these breakers coordinate. And what it comes down to is really needing a vendor coordination table in order to discern if I can get coordination in this area. In some cases, as I'll mention later, there are some coordination tables out there that will also guide you on the non-instantaneous part. But bottom line to understand here is when we say selective coordination, again, per the code definition, or again, the informal industry term of 0.01 second coordination, we're talking about both colored regions have to coordinate to out to whatever the maximum available fault current is. So how do I know in that lower instantaneous region, how do I know if a circuit breaker is going to coordinate? Well, again, circuit breaker coordination tables will guide you in that area. So it is a document that each major vendor produces that will allow you to identify specific breaker pairs and to what level of fault current they would coordinate. Now, different vendors will have different styles of tables. Some tables will be for instantaneous coordination only. That is, the table values tell you the instantaneous coordination, and then everything else is determined by time current curve analysis. And then some tables are designed to give you information on both the instantaneous and non-instantaneous parts of the breaker curves. Now, the typical means of obtaining selectivity in the instantaneous region, and this is not meant to be all-inclusive if there are other newer technologies I'm not aware of, but I think this would cover the large percentage of ways that breakers get coordinated. One way that the tables would cover are simply the design of the breaker and the physics of the breakers in those systems. No special algorithms in the breakers or wiring between those breakers. Another way where an electronic trip unit is involved, say as the upstream and any type of breaker downstream, is there could be an algorithm in that upstream electronic trip breaker that facilitates coordination with downstream breakers, but no wiring between them. And then kind of at another level, there can be, say, electronic trip to electronic trip. You can have algorithms in the trip units that may also require wiring between the breakers. And a typical example of that is something like instantaneous zone selective interlocking. Now, again, every vendor's table will be a little different, but one thing all the tables I'm familiar with share in common is that they're basically organized the same way, in that the downstream breakers form the rows, the upstream breakers form the columns, and where those rows and columns intersect, there's a number, and then that's the number to which the breaker pair coordinates. Now, it's very important when you're looking at these tables, and I'm going to show you one here in an example to make this a little more concrete. There's a number, like I said, many numbers in the tables, but you also have to read any introductory material to those tables or the notes for that tables, because it is very common to have assumptions or specific requirements that go to the table. And I'll give you an example of one here in a second. Now, here's an example of a specific table. This is one we produce in my company. This table shows instantaneous selectivity only. And let me just give you just an example by walking through this one of how you read one of these tables. So on the left-hand side are choices for downstream breakers, right? This is one table of several. So this covers certain downstream choices. Another table might cover different downstream choices. Okay, so there are the downstream breakers. Now we go to the top. This is listing what I've highlighted now in the top, a specific breaker type, the frame type, and then listing the family of trip units that you could use with that breaker that are valid for this selective coordination. Now, one row underneath the upstream breaker family listings, are the sensor options. So now, again, if you're not already familiar with these tables, I'm trying to make you sensitive to the fact that the selection of these breakers is very specific to the things we've already discussed, but also even the sensor size that is with that breaker, because in some cases a breaker can have various sensor sizes. So as a quick example, let's say we have this breaker called the T-Max XT4 as a downstream breaker, and we want to know to what coordination level can we coordinate with, say, an upstream 600 amp sensor T-Max XT5. Well, where the row and the column intersect, there's a number. That number says 100,000 amps. So as long as you've selected breakers that actually have AIC ratings of 100,000 amps, then that's the maximum coordination you could get between those two breakers in the instantaneous region. Now, as I mentioned earlier, there are typically some notes or assumptions or requirements using the table that would be listed in the vendor's document. So do be very careful to read those. And as an example, for the upfront matter paragraph that's ahead of this table, it explains that if the trip unit has adjustability, the trip unit instantaneous pickup must be set at maximum in order for these values to be usable, to be valid. Okay, so circuit breakers can coordinate, and especially for the instantaneous region, using the vendor coordination tables is a vital skill. Let's talk a little bit about specification of selective coordination, because every firm or group that might specify a project does it a little differently, and there are many ways to do it that will work just fine. But the typical question is, do I need to include specifications for selective coordination? Or possibly, should I just leave it to the bidding vendor to decide what to do because they know how to meet the code using their vendor-specific products? The theory being that the vendor knows their breakers the best, so I shouldn't go overboard on specifying it. Well, my bottom line answer to this is you want to do as complete a job as possible to specify the selective coordination. And yeah, there's some basic rules you're going to need to follow to design when you want selective coordination. But use your plans and specs just like you would for any other aspect of the project. Give clear, complete, concise specifications. Well, how do I do that? Well, let me kind of give you a look behind the curtain here from a vendor perspective of what we typically have to do to put things in perspective for you. Remember, as I say, an engineer designer, you may have been working on a project for several months, if not several or a couple of years, and have very frequent contacts. So you're intimately familiar with that project. You know it in and out. But remember, when you hand it off to go out to bid, it probably goes through several hands, and by the time the vendor gets it, they have relatively little time to make quick decisions on who all has to be on the team to propose this, what factories do I need to send this to make quotes, and what are the fundamental requirements, and one of the most important ones being, what are the selective coordination requirements? Because that takes a special skill set to specifically select those breakers. So as an example, we're quickly looking for what version of the NEC is in effect. We certainly like the plans to indicate that and not leave it to individual vendors to determine that on their own. Similar for local jurisdiction amendments, right? If you're aware of something that the local ASJ has an amendment on that modifies something in your selective coordination, it's really good to put that in your specifications. Then, of course, a typical vendor is going to look through the specifications to see what it says regarding selective coordination. What notes are on the drawings about selective coordination? Are the notes on the drawings and what's written in the spec, do they complement each other and are they consistent? If not, calls to the engineer may happen. And overall, is it clear which circuits or parts of the one line require selective coordination? Now, again, when you have been working on a project for many months or like a year or more, all of that will seem very, very obvious to you. But again, keep in mind, the plans and drawings have to be interpreted by another human being who's going to look at this for the first time. So if I were to sum it up from the perspective of the specifier, I'd sum it up this way: the 3 W's, the what, the where, and the why. Before you send your project out, look at it closely and see if you can quickly answer these 3 questions without relying on your in-depth knowledge of having worked on the project, or perhaps you give it to a peer in the office who hasn't worked on the project to see if they can quickly make these assessments. So what level of coordination is required? What definition are we using? Is it 0.1 second? Is it all possible fault currents? Again, the formal definition in the section 100 of the code, what we informally call 0.01 second coordination. Could it possibly be both or neither? That should be very clear and quickly discernible. Where is the selective coordination required? Well, a lot of you will probably say, well, isn't that obvious from, just knowing electrical systems? In many cases, it is. So for example, if you're using labels like ATS-LS, LS is interpreted as life safety, ATS-LRS, legally required standby, that certainly makes it easy to pick out which systems the coordination requires. But I have seen drawings that use ATS-A, B, C, D, etc. And then what's the vendor to do? Well, you could go to the panel schedules and discern the type of loads to figure out what's what, or you could call the engineer. So in my opinion, it's simply better to use, N for normal, E for emergency, ATS-LS, ATS-LRS. That will more readily identify which parts of the systems require the selective coordination. So that and knowledge of the code should produce an accurate bill of material. Now, this last one also may strike some of you as odd, but why is selective coordination required? I put that one there because it is not too uncommon that you'll see requirements and specifications that exceed what the NEC would dictate, or perhaps in some cases are less than what the NEC would dictate. So when one sees that and there's not a clarification to the why, it generates questions. Well, was something missed, something not understood, or is the engineer and owner simply asking for more coordination than the NEC requires, which is certainly allowed? If you're asking for less than what the NEC allows, then there should be an AHJ exemption. So it becomes a bit of an issue. So put the why if you're doing something, especially if you're doing something that isn't standard to code. Which design documents should include selective coordination requirements for the project? So again, we're talking about drawings and specifications. And I'd like to start the discussion with bringing up the power system study spec, right? It's a standard spec that's thrown into projects. Realize that the power system study spec is a service spec, right? It's a study is going to be done and a report is produced and delivered. Whereas coordination requirements are really an equipment performance spec. So now certainly it makes more sense to put the coordination requirements in one location as opposed to saying all the coordination requirements and put that in your switchboard, your switchgear, your panel board spec, right? So it is an industry norm and everybody knows to look in the power system study spec to look for selective coordination requirements. It can also be in the equipment specs, that's okay. But wherever it's put, we want it to meet the tenets and as I discussed earlier, and obviously be clear. Now, one of the things I just want to make sure that no one gets lulled into, just because it's in the power system study spec, right? The power system study engineer is not going to be able to make everything coordinate if the design for one doesn't lend itself to the level of coordination required, and the right bill of material breakers aren't part of what the engineer is using to study. So kind of bottom line here, and this alludes to the points I was making earlier, when we have 0.1 second coordination, it's really achieved, as all these study engineers know, by adjusting any available settings on the breakers you've been given to work with. If I'm going to coordinate to the entire range of available fault current, I really need to make it clear that I'm doing that. So, again, some specs will use the term 0.01 second coordination. And then the study engineer ultimately can only prove the circuit breaker coordination by adjusting device settings and using vendor coordination tables, again, if you want to show coordination for the entire range of available fault current. Now, there are a couple of standard statements in the system study that I want to bring to your attention that, if left unedited, may cause confusion in some situations. And these are the two statements that are in quotes here that I find are in what I would call the canned meaning provided by some national service that provides standard specifications. And the issue that I'm bringing up is look at the terms where it refers to provide adequate time margins. And then in the other statement, it quotes, graphically illustrate adequate time separation exists. As I tried to point out earlier, when we're talking about separation of the curves, that's easy to do from, once you're above the instantaneous region. And that's the skill and technique really that's used to promote 0.1 second coordination. But time separation, you can't do that with typically with an instantaneous part of the protection curve. So the bottom line point in this discussion is if you're not adding something else to this spec or other parts of the spec to clarify you're not looking, if you want, say, selective coordination per the Article 100 definition, if that's what you really want, you do need to add things to the statement, because if I read only these statements and nothing else, it's really telling me 0.1 coordination. Well, what would such a statement or addition to that spec look like? Well, here's what I think is a pretty good example. Actually, has been used in specification. So it identifies, and we're talking about emergency, legally required standby, and healthcare essential power systems. And then it goes on to identify the specific name of the type of system along with the article reference, and then with a reference to the time in seconds. So all of that is great. And then it even breaks out by the particular branch of an essential system of a healthcare facility, what the time standard is for coordination. So this makes it very clear. This is a good spec. The only improvement I would suggest to it is instead of putting, put in there also the addition of the National Electric Code, and if you have already figured out their amendments for the particular project, add that in there also. But the core of it is very, very good and very, very helpful to interpret exactly what the requirements are. And here are an example of drawing notes that I found very helpful, just examples. So selectively coordinate the emergency branch per 2020 NEC Article 700.32. That tells me everything I need to know to select the correct breakers. The example below that, it says kind of the same thing. It doesn't do the code reference, but it spells out in good detail, hey, I want devices feeding and ATS-LS and ATS-LRS and what's below it, and they're going to coordinate to 0.01 seconds. And then it has a note number that's applied to all the breakers that are expected to be coordinated to the standard. So again, that's very helpful by applying the note number to the specific breakers. And then here's another example on the bottom. Manufacturer shall select appropriate breaker types to provide selective coordination for all supply side upstream devices connected to systems containing normal and generator power circuits. Then I really like this statement: coordination shall be demonstrated by manufacturers' published coordination tables. So when they say coordination tables, okay, I know exactly what this engineer is thinking. And then it goes on to make the code references. And then this requirements and assumptions bullet 2 is a very nice one. It says to assume unlimited short circuit current on the primary. That's taking the meant on the primary of, say, your service entrance transformer. And what that assumption included in the spec or note does, it puts everybody on an equal footing that if we assume unlimited primary, we can do an easy calculation to figure out what then the secondary available fault current would be, and then proceed from there to pick the appropriate breakers, as opposed to each vendor making their own assumption as to what the available short circuit current might be, which then would allow different selection of breakers. So these are all good examples to follow. Okay. So that was a little bit about my thoughts on specifications, a little bit about coordination across a transformer. Again, this is a common question I get, and it generally kind of revolves somewhere around this type of question or discussion. I've heard that coordination at a general purpose transformer, and let's say we're talking about your basic, again, low voltage primary, low voltage secondary, but this could be, for example, a 480 to 208 120 transformer. used in many designs. So for such a transformer, I've heard that the coordination starts over. So I only need to coordinate the 208 volt side and the 480 volt side separately, and not worry about the 208 volt to 480 volt coordination across the transformer. Is this true? Well, my answer to this particular question is it's not true, but the element of truth into this is that because of the characteristics of the transformer, it does in fact make it easier to coordinate. And when you look at the time current curve, it kind of guides you toward the thinking that, oh, the coordination across the transformer takes care of itself. Well, it may work out that way, even without explicit effort from the folks involved in designing it or studying it, but it does take a consistent application of the coordination principles, some of which we've talked about, and potentially coordination tables in order to get it right every time. So let's talk through that a little bit. All right, so here's an example of a very simple one line. And let's say there's our general purpose transformer. And if coordination is required, let's say in this example, out to the definition, out to the full available fault current as listed in the Article 100 definition, then branches C and D would need to coordinate with B. Branches C and D would need to coordinate with A, the primary feeder breaker to the transformer. But A and B don't necessarily need to coordinate with each other, because whether I lose one or both, it's going to have the same effect on the system. So what's the role of the transformer in this? Well, the key aspects are, obviously, we have the transformation ratio, where we're dropping voltage, but increasing the amperage ratio. And when I have a fault on a 208 volt side, then I still see less fault on the 480 volt side, and the fault current is limited because of the impedance of the transformer. So impedance is typically between 3.5 to maybe 5.5 or 6% on these types of transformers. That has a very specific effect. So just as a quick example, say this were a 45 kVA transformer, say 2900 amps of available fault current, just considering the let-through current. I'm not going to consider any motors in this basic discussion. So 2900 at the 208 side, that's going to be 1255 on 480 volt. So obviously the 480 volt side is going to see a substantially reduced amperage relative to 208 volt side. And the upshot is here, lower fault currents lend themselves to simpler coordination solutions. So let's tie this together by looking at a typical layout for coordination across a low voltage transformer. So here I'm going to look at a panel board that shows, in this case, I've extended the one line up a little bit. I've got branch breakers D that need to coordinate with the main in that 208 side. So D needs to coordinate with C. D needs to coordinate with B and A, and B and C don't necessarily need to coordinate with each other. So that's the objective we're trying to reach. So let's walk through this time current curve layout and look at the essential points. So again, I'm not showing numbers or settings. The focus is on the concept here. Similarly, I'm not showing the damage curves of the transformer. Obviously, the transformer has to be protected. I just want to show the key concepts here for coordinating across the transformer. So there's my electronic trip main. Again, for this example is really for selective coordination across a transformer for the full 0.01 second level. And typically, electronic trip would be required there. In this case, I'm also using an electronic trip as the primary feeder B. Now on the 208 volt side, again, I'm using an electronic trip breaker. And then on the branch side, there's my thermal magnetic. All right, now the first key point is obviously the 480 volt side devices, they've got to be upstream of the inrush point. So I've done that. You got to make sure that happens, that your upstream breakers are to the right and above the inrush point. Next salient point here is the 208 volt breakers. They have their the instantaneous foot of their breaker truncated, and that's the effect of the impedance of that transformer. So that's a plus in helping us coordinate it. I often call this a stubby foot compared to the elongated foot you get when, say, you don't have as much impedance from the source. The next salient point is here, I've got my upstream devices set above where the downstream breaker has its truncated point due to the transformer impedance. Now, you don't have to do that. You could have it overlapping, but then you're definitely going to be looking at the coordination tables as to, does breaker B in this case actually coordinate for these downstream breakers, and do I have the settings right for that? So in this case, you see how I have a white space now between the 480 volt side and the 280 volt side. So there's no issue with coordination between those breakers in this case. I have no overlap. And that's where the perception is, well, I just do the 208 volt side separately from the 480 volt side, and I don't worry what comes across. Like I said, that it commonly can work out to be that way, but it may not work out that way in every case. You do have to look at this specifically to make sure it works out. So now I've gotten to this point, and really the only decisions left are, well, how do I know these areas of overlap coordinate? And that's where the vendor coordination table would ensure you have to correct breaker pairs and also guide you as to any special settings requirements to make sure this overlap is in fact coordinated. Okay, so lastly, I would like actually not lastly, second to last, talk a little bit about ground fault. Again, another common question. So how do I evaluate selective coordination when one of the breakers, and typically say the upstream, but it could be two levels of coordination, has ground fault protection? So to this point, we've really kind of focused on upstream phase to downstream phase, but obviously there are other combinations that could involve ground fault, as shown as kind of situations 2 and 3, but they're going to be evaluated similarly. The major difference is going to be you now have to consider the combined curve of the ground fault curve along with the phase curve in evaluating coordination with the downstream breaker. Overlap in the instantaneous regions of the phase protection, you're still going to coordinate that just as we've already discussed. So here's a simple example. Again, I'm leaving out numbers and settings to just focus on the concept. This happens to be a 1600 amp main with, say, a 250 amp feeder sitting on the same bus. There's no overlap in the non-instantaneous region, so I know I have at least 0.1 coordination. And when I check the coordination tables for this specific breaker pair, I can determine that they coordinate in the instantaneous region. So these two breakers are coordinated. Now, that was phase only. Let's add ground fault protection to the upstream breaker. And what happens when I do that? Well, I've selected a very low ground fault pickup, and now I've caused some overlap between the upstream ground fault protection and the downstream breaker. Remember, even though the downstream breaker doesn't have its own ground fault protection capability, it will see extra fault current as a result of a ground fault and will respond even with its phase set protection eventually to whatever that ground fault current may be that's added into the current it would normally be seeing. So it's going to be a fault current it sees. It's just not going to be able to react as quickly as the upstream ground fault protection. So in this shaded area I'm showing now, clearly there's a range of amperage where if I have a fault, the ground fault curve is going to commit to tripping and trip before the upstream breaker even commits to tripping. So that area is not selectively coordinated. And again, when I talked about the combined phase and ground fault curve, this is kind of the left edge of that I'm talking about. So you see, I've had that intersection of the dash line with some part of the phase protection downstream. That's what I would like to avoid. And again, the overlap in the instantaneous region, I'm still going to do that the same way with my coordination tables. Now, in the next colored zone, there I don't have a coordination issue because I don't have overlap between the upstream and downstream, and any overlap in the instantaneous region, again, will be handled by coordination tables. So we can adjust the ground fault pickup as shown in this next slide. And the ground fault curve is now put at a pickup setting that allows it to have white space everywhere with the downstream phase protection. So these breakers are now coordinated. some of you may make the point, well, that's awfully close together between the ground fault pickup and the downstream phase, and you're correct. A lot of folks, because of the various assumptions that still go into a study, like cable impedance or cable distances, et cetera, which may not be exactly known, some would like to go over space. So just make sure you're checking your model to see that there may be some other sloping or shaping capability. And here's an example of something that can be done with some ground fault settings to put an additional delay or pickup, and to make the shape look more like an electronic trip unit, to make it easier to coordinate and get, maybe in this case, get a little more space right in there between the ground fault curve and the pickups of the phase protection. So this would be an example of a well-coordinated main with ground fault with a downstream feeder without ground fault. Okay, so lastly, I am going to talk about coordination and the concept of ratios. Before I do that, I do want to point out to Jim and the audience, I have a notice coming up on the computer that Office is going to restart in 10 minutes, not giving me an option to delay. The IT gods are upon me. I'm not sure that's going to affect what we're doing, but if it is, I think I'll be done with this section in 10 minutes, but it may in fact affect the question and answer period, in which case if it does, I will try to resume as quickly as possible. Okay, so instead of, here's the common question, instead of using vendor coordination tables, why can't I just use a rule of thumb for ratios of circuit breakers that will selectively coordinate? Well, let's talk about that. First of all, anything I say here is not meant to, if such tables exist, my comments here are not meant to dissuade you. I'm not aware in the NEMA market that such official documents exist. I did find one for the IEC market that referenced ratios. So please accept these comments as my perspective on at least why ABB hasn't done this yet. So ratios are going to vary by specific breaker families that are involved. Thermal mag to thermal mag cases are going to have a much higher ratio because of the wider tolerances in those type of breakers. E-trip to thermal mag will get a little better, and then E-trip to E-trip may be your lowest ratios because of the tighter tolerances. Ratios for 0.1 second coordination are going to be different than what is needed to get 0.1 coordination. Instantaneous coordination in particular is a function for some breakers, especially the smaller one, branch-like breakers, is going to be a function of the number of poles for some breakers. Okay, so these are just some of the reasons why there'll be very specific cases of ratios that are unique to very specific circumstances. So again, in my opinion, in general, there'll be too many ratios to know or reference. And overall, using such an approach is not going to be easier, and it's going to be less reliable than using time current curve analysis and coordination tables. And here's another major theme here. What ratios am I even talking about? I really didn't define what ratio I'm talking about, and I find that's a common theme when this conversation comes up in any forum. Folks tend to focus on frame separation, but really there are two things that should be considered when we're talking about breakers, because remember, in many cases I can have 2 and sometimes 3 different breaker frames provide the same amperage setting, so you really have a lot of flexibility there. But for breakers, you really need to look at both the frame separation and the amperage separation. So I like to use the term frame separation. I think amperage ratios is okay too, but I think amperage or using ratios for the frames becomes a little difficult or misleading. So let's take those one at a time. You want to talk about frames. Again, every vendor is going to have different rules. I think in regard to frames, we're probably all close, but again, talk to the specific vendor. For the ABB specific case, out of our DET 760, just as an example, if the fault current below the branch breaker is low enough, you're going to get 4 levels of molded case circuit breaker, and kind of as shown here. Kind of your 100 amp frame level, that covers down as low as your 20 amp or 15 amp branch breakers, a 200 amp, 250 amp frame level, so on and so forth. Again, the groupings I'm using, kind of lumping them into the same kind of frame size, that may be different from vendor to vendor, but this is typically how we look at it in my company. Otherwise, if the fault current isn't sufficiently low enough down at the branch breaker, the thing feeding the load, then you may be looking at 3 layers of breakers. Now, based on, again, what I'm showing you here that is specific from our tables, there's a very simple rule that pops out that you need at least 1 frame size of separation. At least 1 frame size of separation. So that's kind of a quick discussion on the frame separation. Now, if I want to look at amperages, let's look at the case again, say where we could get our 4 levels of molded case circuit breaker. When I look at the possible amperages involved, again, remember this 250 amp frame may have a selection down to maybe say 100 amps or so. Where thermomagnetics are involved at some point, right, you're going to have a thermomagnetic feeding your 20 amp or 15, 30 amp loads. That would be typical. The amperage ratios there are typically going to be higher. In a specific case, I know from our own, this 250 amp frame breaker, if it's an electronic trip, with many common branch breakers that would be used at say 208, 240 or 480, you can get down to a 1.6, 1.7 ratio of the amperage setting, and everything will work. But there are other specific breakers that might need, that are used from time to time for specific reasons, maybe a subfeed thermomagnetic. It might need a 2.5 ratio. So again, even within one vendor using different breaker types for different reasons, they're going to be different ratios. Once you get higher up and you start using electronic trips, if this were electronic trip to electronic trip between these 2 frame sizes, here we have the ability, especially with newer trip units with lower tolerances, you can get sub 1.2 to 1 ratio in terms of your amperage settings. If it's an older trip unit or one with less tolerance, you can get down to 1.3 to 1 ratio still. And then again, the higher up you go, probably more likely you're going to use E-trip to E-trip, same thing. You can get fairly low ratios of amperage settings. And here's an example on the left-hand side of a way to space these out to kind of crunch them down to lower amperages. It's often the life safety systems for smaller facilities that provide the bigger challenge, and you have to look at very carefully. The larger systems typically aren't as much as a problem as long as you observe the 3 level, or depending on the fault current available, the 4 level of molded case circuit breaker rules. Okay, so I want to do a quick summary. Again, I see that I'm going to have a forced office update in 3 minutes, so I hope that doesn't affect anything in our connection here, and we'll proceed with the question and answer. But to summarize quickly, please think of the WWW. I talked about the what, when, what, where, and why of selective coordination to make sure that's as clear as possible when you're producing your design plans and bid documents. As hopefully I've convinced you, or you already knew, coordination of circuit breakers is possible even when the time current curves overlap, even if it's in the instantaneous region, and consult the need to consult vendor coordination tables. Coordination across a transformer, you're going to follow all the same principles we talked about, but you do get a bit of a helping hand from the nature of the transformer properties. Where ground fault protection is involved, again, make sure you're looking at that combined phase and ground fault curve when evaluating selectivity with a downstream device. Using frame separation requirements indicated in the vendor coordination tables for coordination in the instantaneous region is a must to be able to consistently produce designs that can be coordinated by vendor offerings. And then in the area of amperage separation, remember you can provide amperage settings on multiple frames. The amperage settings, it will be documented in some tables, not all, but can also be easily determined, especially for the E-trip to E-trip, by just knowing the long time pickup tolerances involved. So at that point, I will stop here. I thank you very much for joining and for your attention, and let's see what questions we can answer.
Good job, Bob. I'm going to show you the question box right now. You should be able to find it now on your control panel.
Let me know, Jim, when I can.
Should be able to open it now.
Okay, so I have the questions section open, and I'm not seeing anything at this point.
Let me read them to you.
Yeah, okay, let's do that.
The first question is, will you be able to share the slides? If you could send me a PDF copy of your presentation, we can link it with the video when it's posted. The next question is the ground fault a kind of short circuit as well?
What I tried to explain was the ground fault curve. You need to evaluate that simultaneously with your phase protection to make sure that combined envelope does not intersect with the downstream device. The one exception there being if you have instantaneous overlap between the phase of upstream and downstream, you can resolve that using a vendor coordination table.
I think that question came in early on, so you probably covered it in addition.
Okay.
Chuck's wanting to know, does Easy Power allow to show the ground fault trip portion of the curve? Look like you use Easy Power for your plots.
I was going to leave that question to you. If you want me to comment, could you repeat the question?
Does Easy Power allow to show the ground fault trip portion of the curve?
Well, yeah, absolutely, and that is in fact what I used in one of my demo slides. Yes, no problem for me showing that on Easy Power.
Then Jack wants to know, what's the reason for some breakers as far as the foot does not stop vertically and it goes down to 0.01 axis?
Okay, so if you're looking at, say, a circuit breaker and you are looking specifically at the instantaneous part of the foot, your observation is correct that in some cases, even the bottom part of the instantaneous doesn't touch the 0.01, if I interpret your question correctly, and that's due to specific algorithms in that particular circuit breaker. If I didn't interpret the question correctly, please ask again or repeat.
Then Louise wants to ask, to use the coordination tables for confirming coordination on the 0.01 instantaneous region, do we need to have minimum added impedance to the cable between these two coordinated cables? It says he understands that the tables are results of tests with added impedance with the coordinated circuit breakers.
Any issues with impedance between the two breakers will show up in your plots as different cutoff points or clipping points for where your instantaneous ends, right? So that would be one impact of the different cable lengths. There is no specific requirement to account for impedance based on what's in the tables. Now, if the X over R's ratios are different than what the standard X over R ratio, which I don't remember off the top of my head, that's used for UL testing of breakers, then I can't speak for every coordination table, at least in ours, there's a description in our document to explain how to account for that difference and essentially apply an adjustment factor to the coordination level.
Okay, so here's another Easy Power question. Chuck follows up previously, does the ground fault trip curve automatically show on Easy Power? And I will answer that. That's basically you need to set up a single line to ground fault, and then you need to select to show either the phase coordination or ground phase coordination to show the ground curve. So there's two settings you need to deal with, Chuck. And then Jack says, is Easy Power default to asymmetrical current? Most CB tables use symmetrical current. So the answer is you get asymmetrical current in the TCC plots and symmetrical current on the one-line diagrams, and you can change either or both as an option.
And it is correct that the tables are based on symmetrical current.
I think that's the end of our question. I apologize, Bob. I think you only caught the tail end of the questions because you weren't an early organizer.
Oh, no problem. No problem at all.
So yeah, if you could make a copy of this, a PDF copy, I think the audience would be able to appreciate seeing that as they view the video.
I'd be happy to send that to you.
Very good job and very informative. Thank you very much, Bob.
Yeah, thank you for the opportunity, Jim, and thank you everybody for joining.
Have a good day.